I forgot my mic, so we'll just have to do without. I just uploaded a few files. This document by Schlenz, he works for Google. He wrote a very good tutorial on PCA. We're going to talk about performing PCA. So on Friday we talked about PCA and its relation to eigenvalues and eigenvectors, right? If you take the covariance matrix or correlation matrix, either of those, you can perform, you can find the eigenvalues and eigenvectors of the covariance or correlation matrix, and your resulting eigenvectors will essentially be the principal components of your data matrix, okay? Here, I have this. Just wondering how much I need to recap on PCA. Okay, so can I zoom? What's going on here? Let me. Okay, so we can perform the principal component analysis on the covariance matrix. Okay, the resulting eigenvalues and eigenvectors. The eigenvectors will be your principal components, and that allows you to, it's a rotation of the data that maximizes the variation. Okay. There's another way to do principal component analysis, and that's with singular value decomposition, okay, which is very closely related to eigenvalue eigen decomposition, but there are a few differences. So anyway, yeah, let's just do a quick overview, okay. So if we talked about, the steps in doing principal component analysis is that you first center your data, okay, so that each column has a mean of 0, and this causes the covariance matrix to end up having just this nice form of x transpose, okay, because basically your mu's drop out to be zeros, and then so you have x transpose, and you're taking the expectation of that, so your covariance matrix has this nice form. And the goal of Pca analysis is essentially to get our covariance matrix to be a diagonal matrix. And the reason why we want to do this is because if you think of the diagonals, that's the variance terms of each column, and then the off diagonals are the covariance terms, okay? And so if your off diagonal elements are very large, that means you've got two variables that are highly correlated, or essentially, there's redundancy in the data, okay? And so with principal component analysis, we're trying to find orthogonal vectors that, will have, by definition, no redundancy, okay? But we want to maximize the variation that's captured. So essentially, at the end of Pca analysis, we want the diagonal to have, we want our covariance matrix to be a diagonal matrix, okay? And this tutorial, it goes into the details of the matrix algebra that tells you how we end up going from, where is it? Okay, and if you're like me, you see a bunch of letters in it, it's a little bit off-putting, but this actually, I think you can follow this with with a pen or a pencil and follow the transformation. And so he's trying to express the covariance matrix of our re-expressed data y as a diagonal matrix, okay? And by making finding basically a transformation using P, okay? And in the tutorial, it ends up saying that this can be accomplished with the Eigen decomposition. Okay, and so with Eigen decomposition, the idea is we've got a matrix A. In our case, our matrix A is our covariance matrix. Okay, which applies a transformation to a vector V, right? And when you find the eigenvectors and eigenvalues, that transformation of A upon V can just be re-expressed as a scalar multiplication operation. Okay, and so so V is our eigenvectors, and our eigenvectors are orthogonal to each other. Okay, meaning there's no linear dependence between them, and so that makes the inverse matrix of V just equal to its transpose. Okay, which is a nice effect, and so this essentially leads us to the Eigen decomposition, which says that any square matrix A can be decomposed into basically three parts, which is V, lambda, V, okay, where lambda are the eigenvalues but turned into a square diagonal matrix. Okay, so normally it's the matrix A multiplied by the vector V becomes a scalar times V, but if we want to just decompose A into different parts, we take our elements lambda and we put them, the scalars lambda, down the diagonal of the lambda matrix here. Okay, and so we have basically decomposed a square matrix A into V lambda V transpose, okay, or V transpose being the inverse of V, which is orthogonal. Okay, and so this is the Eigen decomposition that we talked about on Friday that can be applied to square matrices, which is our covariance matrix or correlation matrix. Okay. Okay. Are you guys familiar with singular value decomposition? Maybe, maybe not. Okay, so singular value decomposition is highly related to Eigen decomposition, okay, except Eigen decomposition must be applied to square matrices, all right? With singular value decomposition, we can generalize this to non-square matrices, okay? And so we can define a few extra terms. So just going back to our Eigen decomposition, okay, we can take an arbitrary matrix X, okay, and we can define, we can take X transpose X, and that's going to end up being a square matrix, right? So you take a rectangular matrix, and then you do X transpose X. The resulting matrix is going to be a square matrix, okay? So this basically sets us up for an Eigen decomposition. Okay, so we're going to just plug in X transpose X, which is square, in for A up here, and this sets us up for Eigen decomposition, okay? But we're going to define a couple new terms, okay? One is going to be basically the square root of our eigenvalues lambda, and we're going to call that sigma, okay? And then we're going to take, we're going to create a new set of vectors that will be our original data x multiplied by from our eigenvector eigenvalue decomposition. Okay, so our v is our eigenvectors. If we multiply our original data x by our eigenvectors and then divide by the quantity sigma here, we're going to define this as a new set of vectors u. Okay, so where does this lead us? Okay, well, we can just re-express this, multiply both sides by sigma, okay, and then we'll have our vectors u times sigma equal to x times our eigenvectors v. Okay, and so we'll define our matrix sigma, capital Sigma, okay, which is the diagonal matrix consisting of sigma. So essentially, the sigma matrix looks a lot like the lambda matrix, except sigma is the square roots of lambda here, okay? All right, so just to kind of illustrate what's going on here, I got this, this actually has a nice diagram here. Okay, so we can take our original m by n, so this is a non-square matrix X, okay? And we're going to essentially multiply it, multiply it by a square matrix M, all right? And so this ends up giving us, on this side we will have an n times m matrix, and then over here we have another matrix U, which is n by n, and the sigma matrix, which has dimensions n by m, okay? And so essentially what we're trying to do is we're trying to re-express our values, our data matrix X times the eigenvectors V as a combination between U and sigma, okay? So this is, U is another matrix, it's a square matrix, different size than this one, okay? This is n by m, and this one's m by n, okay? And you can see that the dimensions line up, and the sigma matrix is essentially the lambda matrix, but taken square roots. But so the difference here is that this thing is not square, okay? So you're going to have 0 elements and some other elements in kind of the places that are off the diagonal, okay? That's not what okay, and so because our V is our eigenvectors, which is orthogonal, its transpose is the inverse, okay? And so this leads us to our singular value decomposition, which is going to be X, and it's U sigma V transpose, okay? So essentially, we want to be able to solve for this, okay? And the computer can do it for us quite quickly. But we're basically breaking down X into 3 parts, okay? U and V are both square matrices, okay? And sigma is not a square matrix, okay? But it's the matrix that allows us to multiply these 3 things together, okay? So U is n by n, sigma is n by m, and V is m by m. Okay, well they all sound the same. Okay, but U and V are basically square matrices. One is n by n, Nancy by Nancy square, and the other one is m by m, Mike by Mike square. Okay, and this one is essentially a diagonal matrix, but it's rectangular, so you're going to have zeros everywhere except for the diagonal. Okay, and so, what ends up happening is that U ends up being the eigenvectors of X transpose, and V are the eigenvectors of X transpose X, okay? All right, so, what does all of this mean? Basically, now we can take rectangular data, or things that are not square, and we can perform basically a principal component analysis, or this singular value decomposition, okay? And then with the resulting data, we can then truncate it, and yes, we'll lose some information, but we can essentially do some kind of data dimensionality reduction here, okay? So I want to show you kind of a neat application of this, okay? In that we could do basically like a rudimentary image compression, okay, with this type of analysis here. So let me clear this out here, okay? So, if you want to follow along, I've uploaded an image called Audrey, and so you'll need a package called Imager. And what this basically does is it takes, oh, you know what? Cancel. I've already I have it installed. Okay, so you want to install the package Imager, okay? And what this does is it reads in image files and it turns it into basically a matrix, right? So if you have a, what are the dimensions of Audrey? It's just a picture of Audrey Hepburn from Breakfast at Tiffany's, okay? So, just a classic photo here. So basically, you can treat each pixel here, and it's grayscale, okay? So we can treat each pixel, well, basically, each pixel is going to be a number from 0 to 255, basically indicating how bright or how dark it is, okay? So if it's black, that's going to be like 0, and if it's white, this is going to be 255, okay? And so we have, what are the dimensions here? What? Ugh, come on. Well, this is, oh, okay, 576 by 719. So essentially, we can express this as a matrix with, 719 rows and 576 columns, okay? Yeah, I guess we don't need to, okay, so install, library imager, okay? Download the image here, and so I'm going to do command load image here. Actually, let me clear out my workspace. Okay. All right, so in my environment, we have so when it's stored as this, so large when you load it, it turns the image into an array, okay? And so normally there's 3 channels in a color image. You got a red channel, a green channel, and blue channel. But this is grayscale, so essentially it's just going to be 1 channel here, okay? And so and if you load like a GIF or GIF, there's also a time dimension in the array, okay? So, but essentially we just want the rectangle, okay? The 716 by whatever, I forget, okay? So, so we can ask for the dimensions of this. Oh, maybe is my image different? I don't know. Okay, 634 by 791. These are the dimensions of the picture with 1 by 1. Maybe I uploaded a slightly different picture. I don't know. Okay, so essentially this is an array. We're just going to extract out the matrix. Okay, so I'm just going to say as.array or as matrix, and then we just want to pull out. We're just going to flatten it out. Okay. Yes. Okay, so this is a 4-dimensional array. Okay, this is like the height, or this is the width. This is the height. I think this one's time and this one's color channel, or maybe these are reversed. Okay, and so if we had a color image, we would have this would have 3 channels. Okay, or 3 dimensions, and then if it was an animation, there would be 1 for each time thing, okay? But it's just a black and white one, and it's a still photo, so this is 1 and 1, okay? And essentially, I just want to turn this into a matrix, which is, I can just, it says large matrix, and we can say, what are the dimensions of this matrix? Oops, not Audrey. We said odd. Odd is going to be the matrix here, and we can ask for the head of our Audrey matrix, or of our odd matrix, and we can see it's just numbers, right? And so basically, towards the I guess this is 791 rows or something. Maybe I should have. I think when we load this, it loads it sideways. Okay. And so basically, it's saying you got something different colors here. Yes.
So the numbers represent like the strength of like black or something in each
It's
pixel?
the so 255 would be white and 0 would be black. Okay? And so this is just, we're representing each pixel as a number from 0 to 255. And if it's 255, it's white. If it's 0, it's black. And if it's something in between, it's a shade of gray. Okay? And so so essentially, we're representing this data as a matrix. Okay. Now, we can treat this as data with 791 variables, right? Okay. Essentially, we got 791 columns and things like that. I think here. Let me transpose this so we'll actually have more rows than columns, okay? All right, so basically we're going to just treat this as 634 columns of data, 791 rows, okay? So basically we have data with 634 dimensions in it, essentially, yes? Yeah, sure. So let me just do a transpose of this, okay? All right, we can center it. We can also, we might not necessarily have to, but okay. So we can take the column means and store that, and then we can center our Audrey data by using the scale function. And basically this just means subtract the column means from our data, okay? Okay, so we're generating huge things in our memory, and so if we were doing this in like 1995, our computer would get angry because we're loading up these giant things in memory here, okay? But it's 2016, so we're okay. Okay, so and we can perform now a singular value decomposition of our centered Audrey matrix, okay? And so that's just using the function SVD, and I'm going to store the results of SVD into S, okay? And so what singular value decomposition does is it produces 3 elements, a U, a D, and a V, okay? So those are, that's basically this. U, the sigma matrix is, it's D, and it's just a vector of value, so we're going to have to turn it into a matrix here. And then V is the other set of eigenvectors here, okay? All right, and so if we looked at any of these, if we looked at S $U and we just ask what are the dimensions of S $U, is that right? U D transpose V. Expecting this to be square, but let me think here. Okay, well, so the singular value decomposition provides our decomposition of our centered Audrey matrix, okay? And then so we can use this to just reconstruct the data, okay? And so if we looked at at this, okay, we would just kind of plug it back into this formula to get back this. And so, this is not exciting. If I were to try to plot any of these things by themselves, it would not make sense. But then when we multiply them together, we end up getting our image back, okay? So you can do U times D times the transpose of V, or maybe I'll make it a little bit easier to see by doing, so this is matrix multiplication. Yes? So S is the result of singular value decomposition, okay? And so, we can ask what does SVD do, and it returns back U and V, okay? And or U, D, and V, and so we can ask for each of these things. So if I ask for S $U, it's just going to be, I'm going to just do the head of it, okay? It's just this crazy matrix, right? Because essentially we have broken down our this is the matrix of the image, right? And we've broken it down into three separate matrices, where one of them is a diagonal matrix, okay? And so the diagonals is S $D, and so this is just 634 values, where it is just the elements of the diagonal of this, okay? But we have to turn it into a diagonal matrix by using just say the diagonal of this, okay? Yeah. No, it gives you a vector, okay? It gives you a vector of this, but we can turn this into a diagonal matrix, okay? Because the diagonal matrix is basically just the vector down the diagonal. Yeah, exactly. That's all it's going to do, right? So, for example, if I just say diag of 1 through 5, it's going to create a diagonal matrix 1, 2, 3, 4, 5 down the diagonal, okay? And so I'm just saying create a diagonal matrix with these 634 values in S $D, okay? And that's going to be stored as D. And then V is just the result of, again, the singular value decomposition. And then so all this is doing, all I'm doing is just saying, hey, if I do the singular value decomposition and then I multiply everything back together again, I get the original data back, okay? And so I can look at, and because I've subtracted off the means, I'm going to add them back, okay? And so we can ask, kind of, what is the head of reconstruction? And I think this should match the head of our original data, or maybe the transpose of reconstruction. Yeah. So. Okay, so if I ask for the head of the transpose of reconstruction and the original data, they line up. Okay, and so essentially, if I now plot this as an image of our reconstructed data matrix, I get our image back. Okay, so yeah, when you load up the Audrey image, okay, it creates the C image thing. And so, if you just try to, when we extracted the matrix and if we just said plot the Audrey matrix directly, okay, it doesn't look like Audrey Hepburn, okay? This is not Audrey, all right? So you have to tell treat using the imager function, you have to say, take this matrix and read it in as values of brightness and whatnot, okay? And then when you produce it, okay, now it's turned sideways here. So that's the default value. So you have to say plot the transpose of this, okay? And yay, okay? So this is not exciting because all this says is singular value decomposition. Yes, indeed that works, right? We've broken out the matrix, and then we said we multiplied it back together, and does it look the same? Yes, it looks the same, okay? But the neat thing, though, okay, is that we can truncate our data, right? So the singular value decomposition, we've got this diagonal matrix with 634 things. What we can do is we can chop this up, okay? And so if I just say, take the first column of U and take the first column of V and use just the first value, the first singular value, or which is basically the square root of the first eigenvalue, okay? And we produce this. This will not look like Audrey, okay? Because we've basically reduced this giant, 634 by 791 matrix into just a single column of values and a single row of values, okay? So we're losing a lot of information, okay? But I'm going to do this, and then just for the case when k equals 1, basically here I'm just saying take the first column. When you give R a diagonal, if you say diag and you just give it a single number, it's going to create basically an identity matrix. So we don't want that. We just want a matrix with one element in it, right? We just want matrix of this where it treats this as a matrix. Okay, so just for the case when k equals 1, we're going to create a truncated matrix U, a tiny truncated matrix D, and a truncated matrix V, okay? So if I ask what's trunc U, it's just a single column. You can't, this is not the way to show it, okay? Okay, it's treating, it's reduced it to a vector, okay? So this is just a vector, and this is a single matrix, and this is a vector here, okay? So we just have a single vector of, 791 values, a single scalar, and a single vector of 600 something values, okay? Okay, 634, all right? But we can use kind of the singular value decomposition to reconstruct our data, essentially, okay? And then so truncated x hat is the result of multiplying those things together. And then so if I ask what's the truncated dimensions of truncated x hat, it'll say, okay, 791 by 634, which sounds reasonable, okay? And we can plot this, all right, as an image, all right? And what this looks like, this does not look like Audrey Hepburn, but essentially, it's saying it's taken a look at this thing, and it's saying, what is kind of the dimension that maximizes variation. No, I can't show a different one over here. And the dimension it has chosen kind of says, this is what it looks like here. Okay, so this is the first Eigen principal component here. All right, and so now I'm going to just delete comment out this line now. Okay, so now that I'm taking the first two, okay, so now, you know, the dimensions of trunk U, okay, we have 791 rows and 2 columns, okay, so essentially I've taken my, you know, 791 by 634, and now I've just taken it down to 2 columns here, and two columns of the other one, okay, and then so I can multiply these together, and we can try to plot this as an image, all right. We can add back the centering information that we subtracted out in the beginning, okay, and this might help a little bit, okay. It still doesn't look very good, right? But as I increase the number of principal components that I use, you know, we'll start to see an image emerge, okay? And so keep in mind what I've done is we've reduced it from essentially 791 rows of 634 variables, okay, which is our matrix for the image. We've reduced it to 791 rows now of 3 variables. Yes, question?
So, like, how do you know what's the optimal, like?
Yeah, you know, okay, so when you do a principal component analysis, you can look at the kind of that diagonal matrix and just kind of see, you know, what's the total variation that exists, and you know, how much of the variation have I captured here, okay? There is not, you know, I guess it's up to you, you know, how much of a loss of information are you willing to accept for the trade-off, you know, there's a trade-off, right? You can simplify your information just down to maybe 3 or 4 key components, but you're going to lose some of the fine detail here, okay? And so, you know, we have essentially 634 or something, over 600 variables, you know. Is it worth the loss of information just to get it down to 4? Basically 4 variables that I'm capturing here, okay? So this is 4, and you'll start to see some of the structure emerge, okay? It's like, does that look like Audrey? Not really, but we're starting to see kind of some of this blobby shapes, okay? So this is the original image, okay? And just at 5, we see a little bit of, you know, there's a big white thing right here, and you know, there's something down here, right? I know it sounds ridiculous, okay, but we've just, you know, we've reduced this basically from 630 down to 5, right? So this is like just a small portion of the actual image. And look, you're starting to see something that looks like eyes here, okay? And you know, you can kind of play around with this, and we're starting to get a little bit more structure here, all right? And so I'm going to just kind of fast forward. So this is at 10, okay? And that looks like a person, right? And this is, again, 634 columns down to 10 columns because of the singular value decomposition, which basically finds these, you know, orthogonal bits of things. So there's no correlation between any of these 10 columns of data, really. It has, you know, tried to maximize the amount of information in the original data that can be captured with just 10 columns, okay? And then so, you know, at a certain point, you know, now we're doubling the information with 20 columns, and we get, you know, a bit more definition here, okay? So here I'm just adding back, so without adding the centering information, we get kind of these stripes in here, and so I'm adding back the centering information to kind of get rid of these stripes. And so this is at 20 of the principal components. Yes.
You know, sometimes you convert like a PDF file or something, and you can choose how many pixels you want. Is that how?
Yeah, it's not. So probably the most common image compression technologies are JPEG and PNG. Neither of those use principal component analysis. They use wavelet transformations, and JPEG uses wavelet transformations and PNG uses something else. I think there was somebody tried to do image compression with PCA, but it didn't catch on. So
Why is it like not good, or it has other inefficiency?
I don't know.
Okay.
I'm not. It's not what's used, but there is this idea of being able to reduce kind of the information required to reconstruct the image. And this almost feels kind of JPEG-y, right? With like if you look like at an image that has been over JPEG processed, you get all of these weird artifacts. And this kind of looks a little bit like that. JPEG does use something else to get it, but yeah, question.
So is there a way for you to like calculate the amount of variance that each component is like accounting for? And what you're doing?
Right. So that comes from our diagonal, the D, which is your singular values D are the square root of the eigenvalues, and the eigen. So now I have to think: do the eigenvalues represent the variance, or is it the? I want to say the eigenvalues represent the variance in PCA, but it might be the squares of the variance or something. But basically, when we look at our singular value decomposition of D, S $D here, okay, I'm going to just ask for the first 50 of them, okay. So essentially, this says this captures this much, and then so you can see there's a large kind of a reduction here, and so I can just plot S $D here, and so you can see almost all of the pretty much all of the information. Okay, this is kind of how much information or how much of the variance is captured with each of these, and you can see in the beginning there's a lot, and then as you add more, you get a little bit more, and then diminishing returns. Once you get 100 versus 200 versus 300, there's not a whole lot more information that you're capturing until you get all of them. Okay, and so we can kind of see like the jump from let's see. So we'll look at what 10 looks like. So that was with 10. Yes.
For your image, like make it look kind of colorful.
Not I can't do colors because there's no color information in the original image. Okay, but so here this is with 20. So that was with 10. This is with 20, and then did not go through. So with 10, I'm going to plot this. Okay, so yeah, that's with 10 principal components. With 20, it looks like this. Okay, we'll jump up to 40. Okay, and that looks pretty good. We can go up to 80. Okay, and that's looking pretty good. Okay, and then we can go back all the way to the original. All right, 634. Okay, so this is the original with everything. Okay, so we have the finest amount of detail, And we can see, you know, what is the difference between using 100 of these, okay, versus 200. Okay, so it's kind of like you're reducing the contrast on the image. It almost feels that way because essentially, you know, contrast, you're increasing kind of the variation, and what's happening is that, you know, by using only 100 versus 200 versus 600, you're losing some of that variation. Okay, and so, you know, when you're down to, you know, if you had 0 principal components, it would just be a gray image, right? There would be no variation captured. Okay, with 1, you're getting some of the variation, and you're essentially reproducing the contrast that kind of exists in the image here. Okay, and so, you know, that's with 200 versus, and I'll jump up to 400, and then so now you have to say, well, is it worth? You know, the difference between 200 and 400 is from here to here. You know, you have to store double the amount of information, right? And so, you know, is it worth that? Okay. So, well, anyway, so this, you know, in your day-to-day analysis, your use of principal component analysis will probably not be for images, okay? Because, you know, we have ways to store images and things like that. But if you think of the image instead, not as an image, but instead of a giant matrix of multivariate data, you know, you got 600 things, 600 variables, and you don't want to have to, it's hard to do any kind of meaningful analysis, and you want to boil it down to just a few, we can see that the difference between carrying all 600 and versus carrying 100, okay, this is kind of the picture of how much information is lost when you go from carrying all 600 to 100, or really the plot of $D. This shows you, you know, how much of the information are you losing. You're not losing a whole lot by, you know, reducing it to a factor of 1/6, even to a factor of 1/10 when you're using just 60. You know, you're losing some information, yes, okay, definitely. We're not going to deny that that's happening, okay, but maybe for the sake of analysis, it's worth this trade-off for this, okay? And so principal component analysis allows you to reduce the dimensionality of your data by, well, first of all, it turns it into creates your covariance matrix into this diagonal matrix of orthogonal components, and then that allows you to then lop off chunks of your data, okay? Because each component is orthogonal, meaning that each one doesn't carry any information about the other ones, okay? You know, whereas before, if you lopped off certain chunks of the data, the other variables, like each column carries information about some of the other variables, so removing a column could have you know, unintended consequences where you're losing more information than what you need, okay? But by making a diagonal orthogonal matrix for a covariance matrix, removing the columns results in just the removal of those columns without the unintended effect of removing information about the other variables. Okay, so that's that. I've got to come up with, the hardest part of teaching you know, a class for the first time is coming up with meaningful assignments, and so I'm trying to think of a good meaningful assignment for principal component analysis. I know on the in the syllabus, I want to talk a little bit about this. In the syllabus, it says we have an in-class exam scheduled, and I'm really struggling with trying to think of a way to test this, and so I know. So I'm, you know, I don't, you know, I'm also responsible to the department to properly evaluate you guys. So I'm working on this. It might end up being like a take-home homework assignment or something that maybe I shouldn't have opened my mouth, but well, you know, just be patient with me, please, as I'm trying to figure this out. I'll make sure it's very fair to you guys, and we'll be okay. Okay. So, you know, the goal is I want you guys to learn these techniques, how to perform them, and some of the understanding of the background theory. So that's my goal. Yes.